Welcome to G Fun Facts Online. Today, we're talking about the silent crisis behind the AI revolution. Artificial intelligence is everywhere, from your social media feed to labs discovering new medicines. But this incredible progress runs on a dirty secret, an absolutely colossal amount of energy. The data centers that power AI are energy vampires, and their thirst is growing at an unsustainable rate. How do we fuel this future without draining the planet? The answer might not be in bigger power plants, but in a forgotten, almost magical property of the tiniest particles in the universe. We're going on a journey into the quantum world to see how a lost property of the electron is about to fuel a new generation of ultra-efficient AI chips. This is the story of Spintronics. For decades, all our computers, from your smartphone to the most powerful supercomputers, have worked on a simple principle: moving electrons around. We create a flow of electrical charge, a current, to represent the ones and zeros of digital information. Think of it like a plumbing system. To represent a 1, you open a tap and let a whole lot of water, or in this case, electrons, flow into a container. To represent a 0, you empty it. This process of constantly moving large groups of electrons consumes a lot of energy and generates waste heat. It's effective, but it's clumsy and inefficient. Spintronics offers a profoundly more elegant solution. It turns out every electron has another property besides its negative charge. It has something called spin. You can imagine it as a tiny, perpetually spinning top. But this isn't just any spinning top. Because of the strange rules of quantum mechanics, an electron's spin can only point in one of two directions: spin up or spin down. That's it. Just two states. This binary nature is a perfect, natural fit for the ones and zeros of computing. So instead of moving a whole crowd of electrons to represent a bit of data, Spintronics allows us to simply flip the spin of a single electron from up to down. It's like sending a signal by flipping a single light switch instead of having to build a whole new power line. This simple act requires vastly less energy. Furthermore, an electron's spin stays put. It doesn't need a constant flow of power to maintain its state. This means spintronic devices are non-volatile. They remember information even when the power is turned off. Imagine a computer that is always on, with no boot-up time, because its memory never forgets. That's another benefit of this new approach. But if it's so great, why aren't all our devices using Spintronics already? Well, the quantum world is a messy place. For a long time, the biggest challenge was a problem that scientists called spin relaxation, or spin decoherence. In simple terms, it's the problem of the lost spin. Imagine you've perfectly aligned a group of electrons, all their spins pointing up to represent a 1. In a real-world chip, these electrons are constantly bumping into atoms and other electrons. These collisions can randomly flip their spins. The perfect alignment you created quickly devolves into a chaotic mess of up and down spins, and your information is lost. The time it takes for this to happen is called the spin lifetime, and in many materials, it's less than a nanosecond. For decades, this rapid loss of spin information was seen as the ultimate roadblock, a source of waste and inefficiency that everyone was trying to minimize. Scientists searched for materials with longer spin lifetimes and designed complex structures to protect the fragile spin states. But then, a team of researchers from the Korea Institute of Science and Technology had a revolutionary insight that turned the entire field on its head. They stopped trying to fight the lost spin and instead asked, what if we could use it? In spintronic memory, the fundamental operation is flipping the magnetization of a material to write a 0 or a 1. Traditionally, this required a large current of spin-aligned electrons, a brute force approach where much of the spin was lost or dissipated before it could do its job. The Korean team discovered that this dissipated spin, this lost energy, wasn't just disappearing, it was creating a reaction force. a kind of quantum kickback. And this kickback was powerful enough to flip the magnetization all by itself. Think of it like this. For years, engineers were trying to design a perfectly efficient rocket engine where no fuel was wasted. This new discovery is like realizing that the hot exhaust gas, which was previously considered waste, could be captured and used to power a second, smaller engine for free. They found that the greater the spin loss, the easier it became to switch the magnetic state. What was once the problem became the solution. This single paradigm shift means we can now design devices that deliberately enhance spin loss to achieve ultra-low power data writing. This breakthrough alone could boost the efficiency of spintronic devices by up to 3 times, paving the way for AI chips that use a tiny fraction of the energy. And this newfound efficiency opens the door to entirely new ways of designing computers, inspired by the most efficient computer we know, the human brain. Our brains perform incredible feats of learning and processing while running on about 20 watts of power, less than a dim light bulb. The field of neuromorphic computing tries to build chips that mimic the brain's architecture of neurons and synapses. Spintronics is the perfect technology to build these artificial brains. In the brain, neurons are the basic processing units, and synapses are the connections between them. Learning happens when these connections get stronger or weaker. Scientists have found they can build artificial spintronic synapses using a device called a magnetic tunnel junction, or MTJ. It's essentially 2 magnetic layers separated by a thin insulator. Its electrical resistance changes dramatically depending on whether the magnetic layers are aligned or opposed. By flipping the spin, you change the resistance, perfectly mimicking the way a biological synapse strengthens or weakens. Researchers have already created spintronic synapses with over a dozen stable states, allowing for far more nuanced and brain-like learning than the simple on-off of a traditional transistor. At the same time, other spintronic devices called spin-torque nanooscillators can act as artificial neurons. They generate microwave signals that are analogous to the firing of a biological neuron. By combining these spintronic synapses and neurons, we can create all-spin artificial neural networks. These are chips that not only compute with spin but are structured like a biological neural network. They can perform complex tasks like pattern recognition with drastically lower power consumption. But the brain-like architecture isn't the only revolution Spintronics is bringing to AI. It's also helping to solve a half-century-old problem in computing known as the von Neumann bottleneck. For over 70 years, almost every computer has been built with the processor and the memory as 2 separate components. The processor, or CPU, has to constantly fetch data from the memory, perform a calculation, and then send the result back to memory. This constant back-and-forth shuffling of data consumes a huge amount of time and energy. It's like a chef in a huge kitchen who has to run to a pantry at the other end of the building for every single ingredient. This is the von Neumann bottleneck, and for data-heavy AI applications, it's a major cause of inefficiency. Spintronics enables a radical new paradigm called in-memory computing. The idea is to perform computations directly inside the memory itself. The pantry doesn't just store the ingredients. It also has its own cutting boards and mixers. The chef no longer needs to run back and forth. Spintronic memory, like MRAM, is perfectly suited for this. Because the state of the memory cell is determined by its resistance, and that resistance can be read without destroying the data, it's possible to design circuits that perform logic operations like AND and OR directly on an entire array of memory cells at once. Researchers have developed systems like computational RAM, or CRAM, that integrate this spintronic computing fabric directly into memory. In tests, these systems have been shown to be up to 500 times more energy efficient and 700 times faster than conventional systems for AI tasks. This is a game changer. It means we could run complex AI models not just in massive data centers, but on edge devices like your smartphone, your watch, or in an autonomous car, all without draining the battery in minutes. When you add it all up, the advantages are staggering. First, the ultra-low power consumption, potentially reducing AI's energy footprint by a factor of 100 or even 1,000. Second, high speed, with switching happening in nanoseconds and the von Neumann bottleneck completely removed. Third, non-volatility, giving us instant-on devices that save power by never truly needing to be off. Fourth, high density, allowing us to pack more power into a smaller space. And finally, and perhaps most crucially for real-world adoption, many of these Spintronic technologies are compatible with existing CMOS manufacturing. This means we can integrate them into the silicon chips we already know how to produce, accelerating the transition. Of course, the road ahead isn't without its challenges. Scientists are still on the hunt for new materials, like 2D materials such as graphene, that offer even better spin properties. Fabricating these devices at the nanoscale with perfect precision is an immense engineering challenge. And designing whole new computer architectures to take full advantage of these quantum effects requires a new way of thinking. But the pace of innovation is breathtaking. The potential rewards are simply too great to ignore. What started as a quantum mechanical curiosity, the spin of an electron, and was later seen as a frustrating source of energy loss, has now been revealed as the very key to unlocking the next generation of computing. We are witnessing the dawn of a new era, one where the subtle, invisible dance of electron spin will power a future that is not only more intelligent, but also sustainable.